So thank you all very much for coming. So yeah, this iTrain is all going to be about FRELLED, the FITS real-time explorer of low latency in every dimension. This is a data visualization package that I've been working on for a number of years, and it's written inside of Blender, which is this software designed for artists. It's got an enormous user base. It's been in development for 20 or maybe even 30 years at this point. And that's really designed for primarily artistic purposes, making CGI images, still images, figures, animations, even game design, that kind of thing. And of course, it's all really geared towards the three-dimensional aspect of things. And I used to be a big Blender hobbyist back when I had still time to do such things. And as soon as I got into astronomy, I immediately wanted to be able to bring my FITS data into Blender because it has such a powerful three-dimensional viewing interface. So FRELLED is an attempt to do that. So the structure of this iTrain is going to be sort of roughly in three parts. The first part is going to be very short. I'm just going to give you a very quick demonstration overview of what you can do with FRELLED, how you can make your data look very pretty, and then just in case anyone has wandered in off the street, that should give you an idea of whether this is something that is of any interest to you or whether you'd be better off using a different tool. Then I'm going to move on. For anyone who has managed already to install this and get it running ahead of time, I will move on to a much slower set of hands-on sessions where I'm really going to walk you through the process step by step. I will tell you every button that I'm pressing on the keyboard. I will make sure you can see the whole mouse movement of which button is being pressed. So if you do have FRELLED already installed, you should be able to follow along with this live and recreate exactly everything that I'm doing on screen. Of course, if you haven't, doesn't matter. You can always come back to the recording and see this walkthrough again later on. I'm not going to mention much in the way of installation. That can either be incredibly simple or incredibly complicated, depending on how fortunate you are. I do want to mention just a very couple of brief little things. So on the wiki, you go down to the installation easy method section. And if you have Windows or Linux, Mac users, apologies, we are still working on a solution for you. Hopefully we will figure something out. But for now, if you're on Windows or Linux, you just download Blender using either of these links. That gives you a prepackaged version of Blender with all the necessary versions of the Python modules that FRELLED requires. You then simply run this one-line setup command, which is basically identical on Linux or Windows. That just does some very simple configurations. And then to configure Blender itself to run, you set up an alias or equivalently a shortcut on Windows. It has these little switches which you need to add to the command. That's not crucial, but it's helpful. It will ensure that the message window that FRELLED generates is always visible, and it will also suppress some somewhat annoying warning messages that Blender generates, which are of absolutely no relevance at all for astronomers and can otherwise be quite distracting. The other little things to mention, well, after that, you simply download the FRELLED package itself from this link. You just unzip it, and that's all. You can then just access the .blend file in there, and I'll show you how to do that later on. The other minor points to mention, though, are on Linux, you might find that the Blender binary is not executable by default. So just like with any other file, just do chmod +x to make that file executable, and then you should be able to run it without any other issues. The other major issue that people have had on Windows is the problem with these JSON files. If you do a Control-F in the wiki and just find JSON, this is the easiest way to find this. What this problem manifests itself in the following way. You will be able to open Blender without any problems, but as soon as you open a FRELLED.blend file, it can instantly crash the desktop with no warning messages. The fix for this is actually really simple. You just copy a couple of files which come provided with FRELLED into the correct directory. So just read in particular this first bullet point in this section, and that should get you up and running really very quickly. Okay, so let me move on to the first demonstration. This one is going to be really just a quick overview of the features that FRELLED can do. Don't try and follow along with this. I'm just going to go through this really quickly. So this is the default file that comes with FRELLED m33.fits. This is an H1 data cube from the Arecibo Galaxy Environment Survey. It's a nice file because it's small and has lots of information in it, and it looks quite pretty. So you can rotate around your data. By default, you get this nice volumetric view of your data. You can toggle between perspective and orthographic mode, so you can really zoom in and out and explore your data from inside out or the outside in, depending on what's more beneficial to you. You can also toggle into this 2D mode. So if you want to, you can still view your data as a conventional series of image slices, which you can see in all the different major projections. One quite fun thing which you can do as well is you can actually toggle a display of this as a height map, so you can actually displace your data, and so that can also enhance your visibility of certain structures. There's a few more things you can also do in the 3-dimensional viewing mode, as well as this standard volumetric display which you get, which is the main thing that I wanted FRELLED to do, because I think this is the nicest way of looking at your data. But you can also see it as a series of ISO surfaces, which you can just enable here. So you get these surfaces at a fixed flux level. Here you see them overlaid on the volumetric data, but you can just simply toggle that off so you can see them as a series of nested surfaces. You get some annoying artifacts in this real-time preview window that you see, but actually when you render them as figures, which I'll be describing in the first hands-on session, all of those artifacts disappear. You get a very much nicer display in the end. You can also turn that display into simple, more plain surfaces, and that gets rid of the artifacts. And you can also just play around with this clipping so that you can hide and reveal the surfaces at different flux levels. Okay, a couple of other final things for this part. As well as ISO surfaces, you can also show contours of your data. So, for example, rentograms plotting contours at fixed signal-to-noise levels per spectral channel, colored by the current spectral channel that is being plotted. You can also overlay images from the Sloan Digital Sky Survey, these RGB images that you can get through the SDSS's Navigate tool. There are various other maps, of course, that you can show as well. And I'll be describing the basic processes of how you set up these maps. And really, once you've done one of these, all of the others should be, I think, relatively self-explanatory from that point on. Okay, so I'm going to move on to the first sort of hands-on session. So if you have already managed to get FRELLED installed and working, then from this point, you should be able to follow exactly how this works step by step. So the way that you organize FRELLED is you first download this zip package that I mentioned from the wiki, and then this will create, you can unzip this anywhere you like, as long as it's not in the same directory as Blender. Anywhere else should be more or less good. This will be your master copy of FRELLED. You will not use these files directly for various reasons. Rather, you will make a copy of these files each time you want to view a FITS file. So the structure that I've set up in this directory is this is my master copy of all of the FRELLED files. And then in these other directories, I've just got 1 or 2 FITS files per directory. The reason for this is that if you just want to view your data with FRELLED and nothing else, then by all means, put as many FITS files in this directory as you like. Go nuts. But if you want to do more of the analysis tasks, FRELLED creates a lot of supplementary files, which will all be put in this same directory. Or as soon as you start having more than one FITS file, there's the risk that you will have naming conflicts between these files, and also it just simply gets incredibly confusing. So it's far easier if you just follow this system of having basically 1 or 2 FITS files per directory. Okay, so we're going to start with the LL Pegasus file that's been provided. I'm going to walk you through the process of not only visualizing the data, but also turning it into a figure which will look something like this by the end of the process. Something that's annotated, suitable for printing in a paper or showing in a presentation. So I go into my FRELLED master directory. I simply select all of those files, apart from the example FITS file, which comes provided. Of course, we don't need that one. But all of the others, I simply copy those files. I then go into the LL Pegasus directory, and I paste all of those files like so. Now, to make life easier on myself, I'm going to rename this FRELLED.blend file to something that's easier to identify as being associated with the LL Pegasus data, so I can just more easily locate it again in the future. So I'm going to call that LL Peg iTrain. And so now I'm gonna, I could in principle open this .blend file here in Windows GUI or through a Linux terminal. I'm not gonna do that because that will negate all of those switches I added to the shortcut or Linux alias. And so that will not necessarily guarantee that I have the console window, and I will get some more extra annoying warning messages, which are not a problem, but just irritating. So instead, what I do is I first open Blender via the shortcut that I created with those switches. And now this is the Blender's standard interface. We are not going to see much of this. To be honest, this is what Blender looks like by default. It has lots of scary looking buttons, which are all about creating three-dimensional models and how to make them look artistic and animated, etc., etc. Instead, what we're going to do is use Blender's own file browser to select that frelled.blend file, the one I just renamed. And this works just like any other file browser. So I just go to File at the top left. Oops. I go to Open, and I can navigate to that directory. So I put that on my desktop. So the system bookmarks include that by default. So I'm going into Desktop, into my demo files, and the iTrain, LL Pegasus. And here is that .blend file, which I renamed just a moment ago. So if I press open.blend file, this will now open the frelled.blend file, which then reconfigures Blender. So what Frelled is doing is it doesn't really suppress all of the features of Blender. Everything that Blender can do is still present. What it does is reconfigure the display. It reorganizes certain of Blender's features so that they are simply not viewable to users. That all of those features which astronomers are never likely to need and will just get in the way and cause distractions, these are all hidden. And all of the features which you do need, but which were otherwise difficult to access in Blender, are now given their own dedicated buttons. So this is the tool shelf on the left. This contains a series of tab menus from which you can access all of the controls of Frelled. And on the right is the 3D viewport, where by default you will view your 3D data in these different formats that I just demonstrated. The tool shelf can be toggled with the T key on the keyboard. If you really want to just view your data and nothing else, you can just toggle that display off and you can bring it back again with the T key once more. So it's really geared around having a nice large viewing area so you can really maximize the display of your data. The other thing to be aware of is the N key on the keyboard. This will summon the properties dialog in Blender, which is used for altering the individual parameters of different objects and also some display settings. You will not need this in Frelled because all of the features here which you do need are already part of these menus. This is really just sort of a warning. If you do accidentally hit N on the keyboard, it doesn't matter. This menu is doing you no harm at all. But if you don't like it, you can simply press N once again, dismiss that. Okay, so let's go through the process of actually loading a FITS file. The way you do this is not using Blender's own file menu as we had before. This will load the .blend files themselves, and they really function sort of as a project structure. These will hold the FITS data and all the other components that we are going to associate with it. To load the FITS file, you go into this main display settings panel at the top in this panel, which is viewable by default. And we use this little folder icon on the right to open another file browser, and then we can select our FITS file. So I'm going to go again, it's through this documents link, and I can go into the demo files directory I created before. Should be in here. So I'm going to use this LL Pegasus converted GIF.FITS file. That really was converted from a GIF. It just happened to be a data set that I really liked, and it's nice for visualization purposes. So it's not a scientifically accurate one. The world coordinate system in this file and the flux scale is all completely messed up. You can't do any science with this data set, but you can make pretty pictures, which is the main goal of this first session. Okay, so all of these buttons, well, if you're really intimidated and have no idea what's going on, you can just simply press this auto import button, and with one click that will set everything you need and load the data with some sensible defaults. The important thing to do is always to bring up this console that comes with Blender. All of the messages that Frelled generates are here. So if you want to see the progress of any operation that you've done, open the console window. And of course, in the very unlikely event that something goes wrong, this is your first port of call. This will tell you any errors or warnings that have been generated. And so that will generate you something like this in around 20 seconds or so for this file. Will vary a little bit depending on system performance, of course. And so before I go through what that has actually done, how that has done this data visualization process, let me tell you how you can navigate around this FITS file. Yeah. So the first thing you probably want to do is just zoom in and out. That's trivial. You can just use the mouse wheel, just like you would scrolling through any other application. If you want to rotate the view, that can vary a little bit depending on which operating system you're using. On Windows, you can just hold down the mouse wheel and then you can just rotate around the view. You get this little delay as it moves to the different major projections initially, but once that data set has all been fully loaded, then you can just rotate more or less seamlessly around your display however you like. On Linux, as things can be slightly different, I think you have to use the Alt and left click. Alt and left click to rotate around instead of holding down the mouse wheel as on Windows. Of course, also pan the view, that is Shift, Alt and left click. That will work on any operating system. I think also if you just Shift and hold down the mouse wheel on Windows, you can also pan the view in that way. But Shift, Alt, left click on Linux, Shift, middle wheel, pan on Windows. The other important thing is ideally you should be using a machine which has a numeric keypad, because then you can use these 1, 3, and 7 buttons on the keypad automatically go in perfect alignment with the major projections of your data set. So 1, for example, gives you the typical sky projection, the XY projection of your data set. You can also use the arrow keys on the numeric keypad, so 4, 6, 8, and 2. They will rotate the view in fixed increments. It's not normally so useful, but it's something that's nice to be aware of. You can also press the 5 key on the keypad, and that is useful because that will transform your view from default orthographic to perspective mode. So then the data is really scaled by the perspective of the viewpoint. And as well as being fun and letting you go inside your data and view this in a rather more visually impressive way, is also genuinely really useful because it means you can zoom in much more precisely on any individual feature, no matter how small that feature might be. And it also, of course, clips out the view of all the data that's behind the camera. So that can make it much, much easier to find a feature that you might be, and locate a feature you might be particularly interested in. And as with most operations, you just press 5 again to toggle that view back into orthographic mode. So, okay, the other thing I should mention is this circular feature you see in the center, this little red and white circle. This is the 3D cursor. You can place that by left-clicking anywhere within in the viewport, and you can navigate as well using this. If you press Alt and Home, oops, I pressed the right button, that will automatically center your view and alter your pivot point around the location of that 3D cursor. Now, of course, it's very easy to get lost if you do this, but there's one feature that will should hopefully remedy that. So if we go into the Analysis tab, so by default, we're on the Display tab for setting up the display of the data. But if we just quickly switch to the Analysis tab, under this Navigation panel section, there's this button, very helpful, friendly button, Center Cursor. That will do exactly what it sounds like. It places the cursor back at the center of the data set. So then I can just press Alt and Home again, and I've recentered, and I'm no longer lost. That's the basics of navigation. Before we go any more into details on that, let me also show you a bit more about how we visualize the data so you can get the most out of your data set. What this auto import button did when we pressed it was to automatically set the values in these 2 boxes, and they control the color and opacity transfer functions, how the values of the data in the FITS file itself are mapped into both color and opacity. Now, in this default case, those are identical. Color and opacity are following the same color transfer function, especially because we use this grayscale color scheme, which is honestly can be the best sometimes because it's the highest contrast that you can get. But for a complicated data set like this, which has a lot of structure filling the entire data cube, it can be a lot more helpful if you use a more complicated color scheme to really distinguish between different features in different parts of the data set. So the first thing we're going to do here is change this. We're going to change this to using this drop-down menu to any of these color schemes, which follow the naming conventions of matplotlib. So I'm going to choose this spectral one. You can choose any one that you like, but I find that this tends to give quite nice results for this data cube. And so how then do we go about setting these values? What are these actually doing? Well, what these are doing is, if you read the tooltips, the value in the left box will control the value of the minimum data level that's being displayed. In this case, any data values in our cube below 59.6 are rendered as transparent and black, so they're basically completely invisible. Conversely, any values in the rightmost box, this 94.4 and above, they will be rendered as saturated and opaque. And so everything above that will have the same uniform appearance. Data values in between these two will be linearly interpolated between these two extremes of totally invisible or totally opaque. We could also use this logarithmic button to use a logarithmic transfer function instead of a linear function. And in some cases, like M33, the default file, this does give much better results. But in the case of this one, I think we can stick with this linear transfer function. Now, how does it know to set these particular values? Well, that is determined by these above boxes, which set the percentile values to extract from the data. And by default, these are set to 55 and 95. But I can change these. So you can change any of these numerical sliders in FRELLED or Blender by left-clicking and dragging within them. Or if you simply single left-click, you can type a value using the keyboard. So I'm going to have 50 instead for this lowest box. And then I'm going to press Tab to go immediately to the next box. And let's try 99 for this. Now, if I press the Get Data Levels button, in a moment, it will update the values that we see here. And these are better, but to cheat slightly, I already know values which look nice for this particular data set. So I'm actually going to type in here directly 50 for the left box and 250 for the right box. And now all I have to do, hopefully, is just press this Load Data button below there, and then I open the console to see the progress, and I just wait patiently for this to load. The loading speed will depend very much on your system performance and the complexity of the data structure. This file should take 20 to 30 seconds or something like that to load. Really large data sets under the worst possible conditions can take a few minutes. So if you can, start with something small to get a feel for how this works. And then this will take just a few more seconds to refresh that as it loads the new display into the video memory. So now you can see we've got a rather nicer display. We've got a much more colorful appearance, which I think is, as well as looking just aesthetically more pleasing, I think you can also actually see more structures present within the data. Now, for this data set, this loading time is probably not too big of a burden to anyone. But of course, if you're doing this repeatedly to try and find the good display values, then obviously you don't want to be pressing load data the whole time, every time you make a change. If you do change these data values, you're going to have to bear with this. But there are a couple of things which you can do to improve the quality of the data display after loading, and these functions happen instantaneously, so you won't have to reload the data every time. For example, you've got this opacity slider. This controls the maximum opacity level of the peak value in your data. So you can just left click and drag within this. And so if you make the opacity much higher, that can enhance the visibility of the faintest structures. And of course, like with the other sliders, you can also just single left click and type a value to enter some exact value if you need to. Below that, you've got the clip alpha slider, and so that will clip the values below the specified opacity level, and that can really make it easier to hide the faintest features and let you concentrate on the brightest features that you can see. I quite like doing this because it looks sort of like a spaceship in this very pixelated view. It really is quite a lot of fun to play with these files. In this case, though, I think the defaults are actually quite nice. So I'm going to set them back to 0 and 0.1. They normally should give you something where you can at least see something of your data to get you started. The other feature I want to mention about how you can control the data display is in this Advanced File Options tab, which is hidden by default, but you can simply click on these little arrows to open them. Oh, another feature I should also mention is if you are confused about what anything does or you want a little bit more documentation, you can always open these little help panels, which will tell you a little bit about how everything works in each individual panel. It can be a lot less intimidating than reading the whole wiki, because I know the wiki is really rather intimidatingly long at this point. So this does a lot of things. I'm not going to go through all of them, but the one feature I do want to mention is this different colors box. So as I say, by default, the opacity and color transfer functions are the same. If you enable this checkbox, that will differentiate them, so that now the opacity transfer function will be set in the same way as before. It will always use these data boxes for controlling the opacity range of the data. But the color transfer function will now be set down here in these two boxes. And I'm going to do another little trick here. So I'm going to set the same values that I had for the opacity, but I'm going to reverse them. So I'm going to have 250 on the left and 50 on the right. And what that will do when I press load data now is reverse the color scheme. So instead of having red for the faintest features, I should have blue for the faintest features and red for the brightest features. So in that way, effectively, you sort of double the number of color transfer functions which are available to you. So it's really designed to try and give you as much control over how you visualize your data as possible. I'm not going to demonstrate that, but if you also notice these export-import buttons, if you have a really large data set and you don't want to spend 5 minutes each time loading it, just disable these. So reduce yourself to one projection, and then that will only load the data from one viewing angle, which of course means you can't rotate the view around fully as you could before, but is much faster. So it's a much better way of getting a handle on whether or not you have chosen sensible viewing parameters for your data. So, okay, this is just demonstrating that, yeah, we are able to reverse that color scheme. I think at this point we can start to move to how creating this into a figure. I think if I remember correctly, I already showed you the example figure that we're going to end up with this nice white background and some simple annotations pointing at the different features, which you wouldn't feel too ashamed of showing to people in a presentation. So I'm going to walk you through the process of how we go about doing that. So we start by pressing 1 on the numeric keypad to go into this sky projection. And you can see this already looks not too bad, but maybe contours would be a little bit more scientific and rigorous than this volumetric view that we are seeing here. The way we can do that is first in the analysis tab. And so we're not going to need this navigation panel for any of this. So we can simply hide that by pressing this little triangle button or arrow button on the left. And instead, we can first open this region setup panel. Regions are Blender objects, and these are sort of the heart of how FRELLED allows you to interact with and analyze your data. And I'm going to be coming to demonstrating more of these capabilities in the next hands-on section, which will be about cataloging features in your data cube. But for the purposes of this one, we're going to select a special type of region from this drop-down menu. The default is a cuboid. We're going to select whole cube. And all that does is set some defaults so that now when I press this add button, it will create a cube of exactly the same size and location as our entire fits file that we've loaded in. It doesn't really appear directly in the data. You can just notice that you've got this light blue outline around the data cube. And you'll also notice in the bottom left, you get the name of this object that we've just created, which is whole cube _001 _ region wire. So that should be active. So so let's start then by creating some contours for this data, and we'll stick with this in the analysis panel. We'll now go down to the region mapping panel, which again is hidden by default. We just click the arrow to reveal that. And let's create a renzogram, which is I think one of the simplest type of contours that you can plot. Again, lots of buttons here, but most of them we are not going to need all of the time. The one we're going to start with is this map type and colors section. This button on the left, if you hit the tooltip, tells you these are the types of maps that you can generate. So I'm going to select renzogram from this drop-down menu. And then above this, you get the parameters for controlling the contours that you plot. The only one we're going to need for renzogram is this leftmost box, which sets the value of the contour to display. So I know in this case that 150 will give me a nice result. I'm just cheating here a little bit. If you are following this live, I would strongly recommend that you don't go below this. 125 should still be okay, but if you go to 100 or below, you will plot so many contours that you're essentially plotting a contour around every pixel, and that will take a very long time indeed. So best not to try that, I think, if you're trying to do that right now. The other boxes, these are useful for other sort of maps, for example, moment zero maps and peak flux maps, which are also available. So that sets the contour step interval and the maximum value, and neither of which we need for renzograms, because renzograms will only plot the minimum value. The fourth box controls the contour thickness. That can be adjusted interactively after creating the contours, so we don't need at all to worry about the value of that ahead of time. Now, we don't need to set any of these other options here. These are all quite sensible defaults. So if I simply press the Generate button, I can now bring up the console to view the progress of that. You can see there are a couple of annoying little warning messages about this no attributes shadeless. This is a completely harmless error that I just forgot to get around to suppressing. It does absolutely nothing. You can also see that some channels haven't found any contours at that specified level. That's completely normal. This will have no consequences at all as long as some contours, some spectral channels do have contours plotted. Of course, if you get a data set where there are no channels found with contours, then you're going to need to change that value. You also see this little warning at the end. That's just because if you are doing a moment zero or peak flux map, then of course you need to have the maximum value to be something greater than the minimum. Otherwise it will crash, but it just automatically sets this by default. Again, for renzograms, makes no difference because we are only plotting the minimum value anyway. So now if we zoom in, we can see it has plotted some nice contours for us overlaid on the volumetric display, and it's given us a color bar indicating what the colors of those contours mean. Now, for making a figure, well, this may be okay, but you might think, well, all of this volumetric display, this is kind of getting in the way of the fits data. So one thing we could do is, of course, go back to our display tab. We could alter the opacity. We could maybe put that down to 0 or something very small if you wanted to. But there's another, I think, more convenient tool, which I just set that back to the default. If you go back to the analysis tab, right at the top in the file section, there's this show fits file box, and then you can simply toggle that to remove the display of the volumetric data, and now you can see only the contours. The other thing I think we should do before we get to making a full figure of this is we can also play with the label sizes. I think these right ascension and declination labels are maybe just a little bit too chunky. In this spectral coordinates tab that we have below this, we've got this label size parameter, which we can alter. I'm going to put that down to 15 just to make them a bit smaller. You can also do the same for the renzogram color bar axis label. This is back in the region mapping panel. Here it's got this TX box. So again, I'm going to just click here and type in 15, and that will keep everything nicely homogeneous. Okay, so let's try and transform this into a more sort of presentation quality figure. So for that, we need to go into the figures menu. And the first thing we can do is change this default that we have. So we could manually alter the background and color schemes, but we can simply also do this by clicking on the preset list, and we can just choose the print option here. And now we have a nice white background and black text, which is much better also for printing figures out. So this is also an environmentally friendly piece of software because you won't have to print so much black ink. Okay. So let's add some labels to this. We can add a label, for example, for the right ascension axis. The way we do that is to first we place the 3D cursor by left-clicking roughly where we want that label to go. By default, it's already configured for allowing us to create text. So we can just change that default text by clicking in this text box here. And I'm going to type right ascension. I almost always spell incorrectly, but for this purposes, I don't care if I have or not. And then I simply press the add button and I wait a little moment for that to appear. Okay, so you see this little blue dot, which is, it has created the label. It's just absolutely minuscule as a default. If we zoom in on it, you can see it's created right ascension, this awful lurid green text, which is much too small, but we can very easily alter that. I zoom back out, I can just use this scale box here. So let's put that to say 20. Let's make that a little bit bigger than the the actual numerical labels. And I can also alter the color using this color picker box. So I just left click in there, and I'm just going to left click in this green, which is the default one, and I just type 0, set that to have nice black text instead. The other thing though is I haven't got a perfect initial guess as to where I wanted that label to be, but of course I can move that around afterwards. The way to do this is to first right click on that object, and now you'll notice that the active object name in the bottom left has changed. Before it was whole cube underscore region, now it's whole cube underscore text. Also check the objects option in the top. That is telling me that one object is selected out of the 199. So now I know I've selected only one object, the correct object, and that when I move this, I will be moving that one and not the region itself, which would be quite bad. Try not to do that. So with this one object selected, to move it, I press G for grab. That will also take a moment to activate. The reason, and now you can see I can just move that around with the mouse. If I position it somewhere which I don't like, as long as it's still active, I can just right click to cancel that operation. Otherwise, if I press G again, and once that becomes active, I can move it. I can just move it around, and I can left click to accept. But the other thing I can do before that is to press, for example, X on the keyboard, and now I can constrain that movement to only the X axis, or conversely with Y or Z, I can move it to those axes as well, and that can be extremely useful. So I'm going to position that over there. Let's just move that down slightly. The reason I should also mention that it's G for grab and not M for move is because M lets you move objects between Blender's layers. This is something you really don't want to do. That can cause problems. So please, this is just something to be aware of. Please try not to do that. And if you do hit that by default, just move the mouse away and it will dismiss itself. Okay, so let's also set up in the same way the declination label. So I just put a cursor over here. I go back into this text box. I type in declination, and I've already got the scale to 20 and the color to black. So this should create me. Oh, yes, this is also important. To create an annotation, you need to have a region selected. The reason for this is that if you are using a more complicated data set where you are trying to map individual features within it, you might have tens of these regions rather than the one that we've got here. And so all of these annotations can, if you're having a really complicated data set, can obscure the view of each other. So you are able to suppress them. You are able to toggle all of their displays on or off. But to do that, each annotation needs to be associated with a region. Therefore, you need to have that region selected before you create one. So as we noticed, of course, that I've already selected just the right ascension text, and that automatically deselected the region. I reselect that simply by right-clicking near where that outline was placed, i.e. along the axes. You can't select the axes by themselves by default, so don't worry about that. As long as you click reasonably near where that region was placed, the outline, then that should give you this selection. Of course, you can check again with the active object name at the bottom. So now if I press the add, it should create me a declination label of the correct size and the correct color. But the other thing I'm going to need to do here is, of course, rotate that. So if I right click to select it, I can now simply press the R key for rotate on the keyboard. And as before, I should be able to move that interactively with the mouse. But in this case, I know that I want to rotate it by exactly 90 degrees. The way I do that is simply, while it's still active, this rotation, is to just type -90 on the keyboard, rotate it anti-clockwise by 90 degrees. And of course, if I want to, I can fine tune the position of this and I can set up the figure much more precisely. In the interest of time, I'm not going to add any other labels to this, but the procedure is basically identical. The only other thing that I want to show you is creating other annotations that you can. So for example, in this menu, you've got others that are available. You've got beam and beam line. These will create you either an ellipsoid or a line of the same dimensions as the telescope beam, as long as those appropriate fits keyword header values are present in your fits data. Otherwise, they will default, I think, to something reasonable. But what I'm going to do here is create an arrow so that we could label the central part of our data. Again, this time I've remembered, so I'm going to select that region before I start collecting creating anything. So I right click on the region. Now I press add. I should create a nice arrow, which I can then use to label major features of our data. By default, the new region that's created is not, it might be selected, but it's not the only object that's selected. So yeah, that's been a bit small. This is I've made my life a bit difficult here, to be honest. I should have placed that arrow outside. But to make sure that's selected, I'm going to zoom in, and then I just right click within the body of that arrow. And now you can hopefully just about see that you've got this blue outline around the arrow. But more importantly, check the name at the bottom. So whole cube underscore arrow. So I know that the arrow has been selected. So I zoom back out, again, just using the mouse wheel. I can press G on the keyboard. Let's move this somewhere more useful. And again, I can rotate this with the R key. Here, I'm just going to do this freely. I'm not going to type in a value. Let's make it like this. Let's make it a nice big arrow. So I can also use the scale here. I can also interactively drag that scale. And then I can just grab that to have it point roughly at the center of the data cube. The other thing you can notice here, though, is that arrow, the view of that is obscured by the contours, because this arrow is itself a 3D object, as also are the contours. The contours are also quite fun to look at in 3 dimensions. But for making figures, you don't want to do that. So the way you do that is to go press 7 on the numeric keypad to go into this top-down view. This is right ascension on the right, the x-axis now, and velocity on the y-axis. So then you can simply press G on the keyboard and press actually Y to constrain the scaling, and then I can move that so that it's now in front of the contours. If I press 1, then you can see, yeah, now I've got a labeled figure with an arrow. So how do we actually go about saving that as a PNG file? That's really simple. You just right click again on the region to make sure that that's the only selected object. And then you press in this region figures panel, the image edit button. What that will do is set up a virtual camera in Blender, which you can use for creating figures and also animations. If you want to create simple turntable animations, FRELLED provides you the capability of doing that in the panel below. That's a little more involved, but I think once you understand this basic process, you should be able, hopefully, to figure all of that stuff out. Okay, so by default, it switches into the view from that camera, and you've got this gray outline, this darker outline, where nothing that will be that's present here will be saved to our final image, and everything within this bright central region, that will be saved in our image file. By default, it's created the camera to have a field of view equal to the size of our region, but of course we've got all these other labels around which we'd probably like to include, so I can simply alter that by typing in the field of view. So let's maybe guess, maybe 500 might be something sensible. These are basically in Blender units, which are essentially pixel, the size of the pixels in the FITS file. That's probably a bit too small, maybe about 650 gives us something nice. And similarly, you've got these controls for the rendered resolution of the image, so the X and Y pixel dimensions. I think about 850 should give us something nice for this image. And then all I have to do is press the Save Image button. If you open the console, it tells me that it's written it, and it tells you where that figure has been stored. So if you go into that directory, it will have created this figures subdirectory, and lo and behold, there's a figure created here, which you can then use in normal way as any other PNG file. Okay, I think that's about it for creating figures. I'm going to move on then to the final hands-on session, which will be about doing the basics of visual source extraction. One other thing that I should mention, actually quite briefly. So, of course, we've gone all this trouble of now setting up this file. We can, of course, simply save this. And if I simply go File Save from Blender's menu and I close that, I can go back into Blender and reopen it. It will be the top of the recent file list. Everything that we've just done still exists. So we don't have to reload the FITS data or even set up our figure. But there is one irritating little glitch where it doesn't always refresh the display of the colors of the screen correctly. But that's easy. We just go back to the Figures tab and we turn it back into the screen display mode or the print display mode, whichever one we prefer. The FITS data is also still in here, but you've also got all of this other stuff like this arrow and the contours, and we might want to suppress that. There's a very easy way of doing this. If we just right-click to select the region, we go into the region figure management panel, and we simply press hide this one, and that will hide everything apart from the fits data and its axis. Go back to the analysis panel, re-enable the show fits file, and here is our fits data. So we can just have a nice clean inspection of the data once again. We don't have to go through all the trouble of loading the fits data that we had to begin with. Okay, so let's go on to the second final hands-on section, which is about visual source extraction in this second data cube, which is the NGC 2903 dataset from FANGS. So just as before, I'm going to go into my master copy of the FRELLED files. I'm going to select all of these files, apart from the M33 files. I copy them all. I then place them in the NGC 2903 directory. Now here you are provided with two fits files. One is larger, one is smaller. One is just a truncated version of the other one. Just in case, if you are having problems with the large data sets, then you can try it on this small one. It's a lot faster to work with, especially if you have lower end systems. Although, to be honest, I think this is basically not a concern for anyone these days. It's there just in case. So, okay, as before, I'm going to rename that frelled.blend file just so it's much more convenient for me to find. So NGC 2903 iTrain. Now, in the same way as before, I open Blender, I open a file browser, and I navigate to that file that I just renamed a moment ago. So demo files, iTrain, NGC 2903, and I open the iTrain.blend file. Now I'm going to cheat even more than I did before here, just in the interest of saving time. So I open the file browser once again to find the fits file. I go into NGC 2903. I select the fits file I'm going to use. I'm going to use the larger file. Feel free to use the smaller file if you prefer. And I already know ahead of time some data values which will give us a nice display. So I'm going to set 1 and 10 in this case. And I'm also going to go for spectral. And just like before, I'm going to reverse that color scheme for the colors themselves. So I enable different colors. I type in 10 here and 1 in this box. And then I simply press load data and wait for that to process. Now, these values of 1 and 10 are provided because this is a data cube which has been recast into signal to noise format. So what I did was divide each spectrum by its own RMS, which effectively gives you the signal to noise values of the cube. You can do that with a script which comes provided in FRELLED. It's in the extra scripts directory. It's this ages cleaning.script, which does several other things. If you read through the introduction to that, it should be explained to you how to use that. You just provide it with a fits file and set some basic parameters, and that should convert your file for you. Okay, so that looks not too unreasonable. I think maybe we can just boost the opacity a little bit. Maybe 0.2, I think, should give us a little bit of a brighter display of our data. Again, as we rotate around, it might take a second or two to update, and after that, we should get a nice seamless rotation. The other thing I'm going to do with this data cube is also load it into the 2D display mode. So I now just go into this 2D toggle, and I'm going to simply change this lower data value to -1, because in 2 dimensions, I don't care about the faintest features obstructing my view, which is a problem that you might have to deal with the 3-dimensional display. In 2D, 2D is much better for seeing the really faintest features, so you can even get away with the negative values in this case. And just to demonstrate that this can be done, I'm also going to change this to grayscale mode, and I'm going to turn off different colors here, and then I simply press load data. And once again, I wait for that to load in so I can at least show you the basics of using this 2-dimensional display capability. Again, it takes a similar sort of time to load 2D as 3D, and you can toggle back and forth between them once they're both loaded. So in 2D, you can pan through the channels using this timeline button at the bottom. So you just left click and drag within that to find different spectral channels in this projection, or position velocity maps if you're using the other projection. So for example, if I go into the XZ projection, the right ascension velocity projection, then I can also zoom out using the wheel to show the full range of the channels or positions that I can scroll through here, and I can do that in exactly the same way as before. So let's start though in 3D mode. So I simply press that toggle and I go back into 3D mode. And I don't know all of the ins and outs of the science of this data set. So this really is just a demonstration to show you the point of principle of how we would go about visually cataloging a complicated data set like this one. Let's say I wanted to catalog all of these little red blobs, which I presume are CO molecular clouds in the NGC 2903 galaxy. So let's say I want to catalog this feature. I want to remember that there is a cloud at that particular position. Well, all I do is left click with the mouse wheel to place the 3D cursor on the center of a blob. Of course, I've done that in the sky projection, but that doesn't guarantee that the cursor is positioned at that exact position in 3D space. There's a couple of different ways I can ensure that that will be the case. One is to press Alt and B on the keyboard, Alt and B, and then you get this crosshair which appears. And now if I left click and drag around that, I define this region which restricts my view to this column of data along that line of sight. So now if I go into the 7 projection, the XZ projection, now it's easy for me to scroll along and find that particular blob without having the view of the data in all the other projections getting in my way. Now, of course, I probably want to toggle that back, so I simply press Alt and B again, and that restores my full view of the data. To actually create an object to mark that, I go into the Analysis panel. I go down to the Region Setup panel once again, and now I leave it at the default cuboid region. I'm going to give it some name so I can remember what this is. I'm just going to call it blob, and I'm going to press add, and that will create a cuboid region called blob_001. If I zoom in on this, well, I probably need to rescale this to make sure that it's going to mask my view of this blob completely. I'm just going to use a simple cuboid, or perfect cube in this case. You can also rescale along different axes. So if I press S and X, I can constrain that scaling. Again, if I don't like the scaling, I can right-click to cancel that operation, or S and Y, scale along the spectral dimension. In this case, I think a cube itself is perfectly okay. So S for scaling, B for grab, R for rotate. Works the same for all objects in Blender. I can also toggle the display of this. So by default, it's this hybrid mode, but I can also press wireframe. So now I've just got a wireframe outline, so I can instantly see which features are identified, and I can see that data itself. But for making a catalog, it's probably better if I hide this from view as much as possible. So there I can use this solid display mode, and that will simply render it as a perfectly black cube. So all of that data and its outline is hidden. Hybrid mode, which is the default, shows you the outline, but also hides the view of the data within that. So I'm just going to create a couple more just so you can get a feel for how this is done. Let's try this one over here. I've placed the cursor again in sky projection mode. The other handy tool that I have for making sure that the cursor is the correct position is in the navigation panel. There's this peak cursor button, and that will put the cursor at the location of the peak flux along the current line of sight closest to the major viewing projection. So now it's pretty much bang in the middle of that cloud. But I can then press add again, and you will notice it will update the counter at the bottom. It creates this active selected object with this bright outline, and we've got the name of the current object, blob_02. It has this conventional naming syntax because I really don't like the coordinate-based naming syntax that people use, which has these awfully unpronounceable names. I just really don't like that. So I'll create one more just so you can get a feel for this, and you can hopefully see that this process becomes really very, very simple. It becomes quite trivial to create maps or catalogs of hundreds of data sources, depending, of course, on the complexity of your data set. But it means that visual extraction now becomes possible for quite large data sets. So how do I go about using these objects? Well, I can create maps of them in exactly the same way as I showed you before in the earlier demonstration. So I could create maps of the SDSS RGB images, which will be plotted with inside FRELLED here, or I could create contours of these objects. I can also, if I want to, I can toggle which one's already selected. So by default, the last object that I created is selected. I can toggle that on the keyboard with the A key. That will toggle the selection status of all objects. So if you can see if I keep hitting A, I either toggle all on or all off. I can also do that if I press A so that they're all unselected, they all have these white outlines. With the counter at 0, I can press this button and that will reselect all of them. And if I press it again, it will toggle them. If I now adjust that counter, let's say to number 2, that will alter so it selects blob number 2. Here's a little point that I think is really worth bearing in mind. There is a difference in Blender between active and selective objects. Active objects are the one that you're currently working on, and that any operation to manipulate that object will apply to the active object. But the select button only causes the selection state to change, and that's not the same as the active state. So blob underscore 3 is active, but blob underscore 2 is actually the one that's selected, and that is a little bit confusing. The way to try and disentangle this is, if I start from a fresh one, is in your head and say, you can see that blob underscore 3 is still actually active here. But if there's nothing selected and I just select blob 2, well, now I know that this is the object I'm interested in. If I want to make that active, I simply then can right click near that object and that will become active and updates its label in the bottom left corner. I can also change the color of these objects with the color picker. So let's just make that one red, and this one I can just right click to select, and let's make that yellow. And you can see how if I gave a different naming prefix, I could select regions of different types. So if I had outer blobs and inner blobs, I could select them all and give them all different colors all at once. So you can really make quite detailed catalogs of your different object types in that way. The other thing I can do is if I select all of these objects, I can press this export button. And what that will do is create basically a crude catalog in the main directories. This WCS mask file contains the name, the right ascension, declination, velocity, and velocity width of your objects, which you can use as a catalog. You can also go the other way around. You can use the import button. If you create your own catalog of objects with the same syntax, which is a very simple syntax, you can import as many of these different regions as you want. So you can do a visual extraction and combine it with an automatic extraction. So you can verify the result of, say, a visual extraction by visually inspecting how they appear in the data set all at once. And this means that you never really need to know the coordinates of your data because you can extract them all directly with this import button. You can also use the navigation panel up here, which I think should be self-explanatory. If you press the Where Am I button, this will tell you the location of the current 3D cursor. You can also reposition the cursor directly on the position of an object with Shift and S on the keyboard, Shift and S, and then you go down to Cursor to Selected. That will position the cursor at the center of the object, and then you just press Where Am I to update the coordinates. Conversely, you can also do this if I position the cursor somewhere else. If you do Take Me There, it will position the cursor at the specified location. It also comes with a name resolver which uses AstroPy to resolve the name of common objects, and it will update at least the sky coordinates of the objects for you. I think that's pretty much all of the basics that I wanted to go through. There are probably hundreds of other little features which I've forgotten to mention, but I think that should give you the gist of how you use it and how you use the interface. From this point onwards, if you've managed to follow this so far, everything else that FRELLED can do should hopefully be reasonably self-explanatory for you. Don't forget, of course, there's the wiki. There's also the video tutorials on the wiki, which will walk you through step by step of every operation that you can do. So I think at this point we can hand over to the Q&A section. So yep, thanks everyone again for participating. I hope at least someone was able to follow along live, but if you weren't and you have any problems, please don't hesitate to get in touch with me via email. Okay, thank you.